Welcome to Chapter 5 Introduction to SQL or SQL. Let's learn together, and after this week, we will actually get started with either SQLite or MySQL. So let's jump into this. We will be defining terms, interpret the history and role of SQL in database development. We'll define a database using SQL Data Definition Language or DDL. Write single table queries using SQL commands. Establish referential integrity using SQL. Discuss the SQL 1999 and SQL 2016 standard. Structured query language, often pronounced SQL, the standard of relational database management systems or RDBMS, where RDBMS is a database management system that manages data as a collection of tables in which all relationships are represented by columns, values, and related tables, such as a clinical system has a patient ID, patient name, and all the issues that patient has been facing in terms of health and all the bills and everything associated. However, that database is not applicable in the airline or travel industry. 1970, E.F. Codd at IBM developed relational database concept. Between 1974 to 79, System R with SQL, later called SQL, created at IBM Research Lab. 1979, Oracle markets first relational DB with the SQL. So the concepts of relational database technology were first articulated in 1970 by E.F. Codd's classical paper, A Relational Model of Data for Large Shared Data Banks. System R was a project at IBM Research Laboratory in San Jose, California that demonstrated the feasibility of implementing a relational model in a database management systems. They used a language called SQL. It has later been named SQL, but SQL is still often how it is pronounced. SQL 92 was a major revision and was structured into three levels: entry level, intermediate level, and full level. SQL 1999 established the core level performance and conformance, which must be met before any other level of conformance can be achieved. Core level conformance requirements were unchanged in SQL 2011 or SQL 2011. In addition to fixes, the enhancements of SQL 1999 and SQL 2003 introduced a new set of SQL XML standards. Three new data types, various new built-in functions, and improved methods for generating values automatically. SQL 2006 refined these additions and made them more compatible with XQuery and XML query language, published by World Wide Web Consortium W3C. SQL 2008 improved analytics query capabilities and exchanged merge, MERGE, for combining tables. The most important new additions to SQL 2011 were related to temporal databases, that is, databases that are able to capture the change in data values over time. At the time of this writing, most database management systems claim SQL 92 compliance and partial compliance with SQL 1999. And SQL 2011-2016 added row pattern recognition, JSON support, Java Server Object Notation, polymorphic table functions, and an extended set of analytical capabilities. A SQL standard, it is no longer certified by the U.S. Department of Commerce National Institute of Standards and Technology, which is NIST. sets. I have skipped few slides because SQL 2016 is the standard that we are using now. A database instance, also called a database server, is a set of memory structure and software processes that manage the access to a set of database files. Each instance maintains one or more database cells organized into catalogs consisting of schemas. Here we see an instance of a DBMS along with two databases, prod and dev. The production database contains its own data indexed by catalog prod C. It is the actual database being used for business operations. Development database is used for making application changes and testing. Usually organizations have two separate databases, one for production and one for development. The SQL environment is a space where SQL statements are executed. It is like workspace where you can manage and manipulate data stored in databases. Imagine it as a kitchen where the ingredients are the data and recipes are the SQL statements. And the dishes you prepare are results of your queries. In this environment, you have several components like schemas, catalogs, SQL Server modules, SQL client modules, and SQL routines. One of the key components is the schema. The schema is like a blueprint of the database. It defines the structure of the data, including tables, views, and indexes. For example, if you are creating simple library system, your schema might include tables like books, authors, and members. You can create schema using the create schema statement. Here is an example that you can use as create schema library. Another important part of the SQL environment is the catalog. A catalog is named collection of schemas. It is like library that contains different books, schemas. Catalogs help organize, manage schemas. For instance, you might have a catalog for your personal projects and another for your work projects. So you can also create a catalog like create catalog my projects. SQL Server modules and SQL client modules are also part of SQL environment. They are a collection of SQL routines and other objects. Think of them as cookbooks and contain different recipes or routines. These modules can be executed to perform specific tasks. You can write a module like create module, my module as procedure, and the list can go on, and then you have to end it by writing end module statement. Lastly, SQL routines are like the tools in your kitchen. They are reusable pieces of code that perform specific tasks. They can be procedures or functions. For instance, you might have a routine that calculates the average routine of books in your library system. All these components work together in the SQL environment to help you manage and manipulate your data effectively. They provide structures and set of tools to interact with your database. So again, you have looked at the given pictorial representation. That is the SQL 2016 standard. A string is a character, varying character with a certain number. Binary is a binary large object or blob. Number is numeric. Precision scale, decimal is P and S, which is precision scale. Integer, temporal is timestamp. Timestamp with local time zone. Boolean is true or false. DDL, DML, DCL, and the database development process. Let's look into this with a few examples. First, creating a table is a common DDL operation. Imagine you're setting up a new filing cabinet in your office. You decide what kinds of folders, which technically are tables in database, you need and what information, that are the columns. each folder will contain. For instance, you might create a folder for employees with sections for ID, name, position, and salary. This is similar to creating a table in the database where you define a table name and its columns. Another DDL operation is altering a table. Picture this: you have been using your employee folder for a while, but now you realize that you need to add new sections for email because you want to start storing the information as well. So you add new section in your existing folder in the database. That is like altering a table and adding a new column. So the physical design of DDL is create tables, indexes, views, establish foreign keys, drop and or truncate table is a physical design. This is also maintenance, used in the maintenance also. Lastly, dropping a table is also DDL operation. Imagine you have a folder called old projects that you no longer need because all the projects in it are completed and archived elsewhere. You decide to remove this folder from your filing cabinet to keep it organized and free up space in the database. This is similar to dropping a table that is no longer needed. You remove the table and all its data from the database. Now let's look at DML. Inserting data into a table is a common DML operation. Imagine you have a notebook where you keep track of your friends' contact information. Each page in the notebook represents table and each line on the page is a record. When you make a new friend, you write their name, phone number, and other details on a new line in the notebook. This is similar to inserting a new row of data into table in a database. Another DML operation is updating data. Pictures this: you look up friend's phone number in your notebook and realize it is outdated because you've gotten a new one. You cross out the old number and write the new one next to their name in the database. This is like updating existing data in table. You change the value of a specific column for a specific row. Lastly, deleting data is also DML operation. Imagine you have a friend who moved away and you no longer need to keep their contact information. You find their detail in your notebook and cross out the entire line in the database. This is similar of deleting a row of data from the table. You remove the entire record from the table. These operations allow you to manage and manipulate the data stored in the database tables. Now let's look into what DCL does. Data control language, as I just mentioned, DCL, is a subset of SQL used to control access to data in database. Granting permissions is a common DCL operation. Imagine you have a private library and you want to allow a friend to borrow books from a specific shelf. You give them the key to that shelf, permitting them to access the books there. In the database, this is similar to granting permissions. You allow a user to perform certain actions like reading or updating data in specific tables. Another DCL operation is revoking permissions. Picture this as you previously allowed a friend to borrow the book or books from a shelf. Now that you decided you no longer want them to have the access, you take back the key to that shelf in the database. This is like revoking permissions. You remove a user's ability to perform certain actions on specific tables. Managing roles is also DCL operation. Imagine you have a group of friends who all have the same access to the library. Like being able to borrow books from any shelf, instead of giving each friend individual keys, you create a library member role and give everyone in the group the same key. If you need to change their access, you just update the role in the database and assign, like this is similar to managing the roles. You create the roles with a specific permission and assign users to those roles to simplify access control. These operations help you manage who can access and manipulate the data in your database, ensuring the data security and integrity. This is also called role-based access control or domain-based access control. So the data definition language is measure, create statements, create schema, defines a portion of the database owned by a particular user, create table, defines a new table and its columns, create view, defines a logical table for one or more tables or views. Other create statements are character set, collation, translation, assertion domain. Steps in the table creation. I would suggest you to read the book that is provided with this course. This will allow you to look into all the 7 which are mentioned, identifying the data type of attributes, the columns that can and cannot be null, columns that must be unique, the candidate keys, primary key, foreign key mates, determine default values, identify constraints on columns, domain specification, create the table and associated indexes. Let's look into a few examples. Creating a table in database involves several steps as mentioned on this slide that ensures the table is well structured and serves its intended purpose. You need to define the purpose of the structure of the table before you even jump into creating a table. This involves identifying what kind of data the table will store and how it will be organized. Think of it like planning a new filing cabinet for your office, as I just mentioned earlier. And that will actually tell you about the employee ID, name, position, and salary for each details that come in the column. And you specify the data types of the columns. Which this step is like deciding what kind of information go into each section of your folder. For instance, the employee ID must be the number, and the name must be the text, and the salary might be a decimal number. In the database, you assign data types to each columns to ensure that the data entered is appropriate and consistent. So let me repeat myself, that the data types to each column to ensure that the data entered is appropriate and consistent. This is significant, that's why I repeated it twice. This helps maintain data integrity and make it easier to perform operations on the data later. Finally, you create a table using a SQL command. This is like actually setting up the filing cabinet of the folders in your office. You use create table statement to define the table name, columns, and their data types. You can also add constraints at this stage, such as making a column mandatory, not null, or setting a default value once the table is created. You can start inserting the data into it. For example, you might create a table called employees with columns, employee ID, name, position, and salary, each with its specified data type. By following these steps, you ensure that your table is well designed and ready to store and manage data effectively. So general syntax for the create table statement: use the data definition language. This figure shows the overall structure of create table statement. It shows that a table will have a name and some number of columns definitions and table constraints. In the following slides, we will see several examples related to the Pine Valley Furniture database that we are working for a while together. So the ER diagram from chapter 1, each of these entities, including the associative entity, is implemented as a table in the database. So customer has customer ID, customer name, customer places an order. So order has order ID or customer ID that is coming from the customer table, and order date. So the order has been placed by a customer or customer places an order. The order contains order line quantity. Order line quantity is contained in the order with the order ID, and product ID. Product has product ID and standard price. So product has an order line in terms of quantity. So here we see the SQL DDL commands for creating 4 tables, one each for customer, order, product, and order line. Note that each of these, there is some number of columns definitions and some number of constraints. So I would suggest you to try creating these tables if you have already downloaded SQL Server and Workbench. This will allow you to look into how create table customer T is actually created by having customer ID. Number is 11, 0. The customer name, the varchar 2 with 25 set of characters in it. Customer address, varchar 230. Varchar 2 is a certain attribute type. Customer city is varchar 220. So up to 20 characters can come in a city's name. Customer state, character 2, and customer postal code, varchar 9. So why varchar? You might be entering a Canadian customer postal code. That is different than the US postal code. And US postal code also is 5 dash, and then there are 4 more numbers. Create table order T, order ID, order date, customer ID, and constraint order primary key. PK is primary key order ID. Constraint order FK or foreign key is customer ID, references customer T from customer ID. So you can see the constraints are technically linking two different tables together. And then you create table product T, and then you go create table order line T. So you can write all the constraints in order line T by linking all the other tables within the order line T as one joint transaction table. Defining attributes and their data types. Creating product T has product ID, product description, and product finish. None of them would be not null, because if product ID is null, then it means there is no product that we are looking into. And then check product finish in cherry, natural ash, white ash, red oak, natural oak, and walnut. That is product finish in. So that's a check that we have put in that table. Product standard price, decimal 6, 2. So up to 6 values, and then 2 cents. The 50 cents up to 99 cents. Product line ID is integer. Constraint product PK is primary key product ID. Non-nullable specifications. Some primary keys are composed of multiple attributes. So create table order line T has order ID, not null, product ID, not null, because if you are placing an order, you must know the product ID to place an order. And order quantity is 11.0. Constraint order line PK with primary key order ID and product ID. I would suggest you to give it a shot if you have already installed SQL Server and Workbench. Controlling the values in attributes. So order T has order ID, order date, whereas order date is date default, sysdate. Sysdate is the system date. So controlling the values in attributes is significantly important. Let me share a couple of examples for you to understand more. So before I go into examples, here we see the domain constraint that limits the number of allowable values for the product finish column. The check operator always ensures the update and insert attempts to this table will only allow the value listed. However, because product finish does not prohibit null values, it is possible to insert a record while leaving product finish without the values at all. We also see a default value for order date, which is sysdate. Sysdate is the current date. So if a new order record is created and the order date is not explicitly entered, then the default to the current date at the time of the record is created via an insert statement. Identifying foreign keys and establishing relationships. Here we see that the order table has foreign key. This constraint statement creates a foreign key constraint referencing the customer table's primary key. Let's look into this in a little bit more depth by having a few examples other than the creating the table of customer T. Identifying foreign keys and establishing relationships between tables is a crucial part of the database design. The first example I like to share with you is hospital management system, where the tables are patients, doctors, and appointments. In the appointments table, you would have foreign keys referencing both patients and doctors. Each appointment is linked to a specific patient and a specific doctor. This establishes many to many relationships between patients and doctors through the appointments table. Next example is travel agency, where the tables are customers, bookings, and flights. In the bookings table, you would have foreign keys referencing customers and flights table. Each booking is linked to a specific customer and a specific flight. This establishes a many to many relationship between customers and flights through the bookings. Next example, we can look into an entertainment platform such as Netflix or Amazon Prime or Paramount Plus. The tables are users, movies, and reviews. In the reviews table, you would have foreign keys referencing users and movies tables. Each review is linked to a specific user and a specific movie. This establishes a many to many relationship between users and movies through the reviews table. Next example can be e-commerce, where customers orders and products, which Pine Valley also is one of the examples. And in the table orders, you would have foreign keys referencing customers table. Additionally, you might have an order item table with foreign keys referencing to both orders and products. That is, order line can be one of those tables. Each order is linked to a specific customer and each order item is linked to a specific product. This establishes a many to many relationship between orders and products through the order items. The last not the least, since we are in the university, let's take a university educational institution system. The tables are students, courses, and enrollments. In the enrollments table, you would have foreign key referencing students and courses tables. Each enrollment is linked to a specific student and a specific course. This establishes many to many relationships between students and courses through the enrollments. In each of these examples, foreign keys are used to link related data across different tables, establishing meaningful relationships that reflect the real world interactions between entities. This approach ensures data integrity and allows for efficient querying and management of the databases. Data integrity controls. Referential integrity is constraint that ensures that foreign key values of a table must match primary key values of the related table in one-to-n relationships, restricting delete of primary records, update of primary records, insert or of dependent records. Let's look into a few examples of data integrity controls to understand it in more depth. Data integrity controls are mechanisms and practices used to ensure the accuracy, consistency, and reliability of data within a database. These controls help prevent errors, inconsistencies, and unauthorized changes to the data. Let's discuss 5 data integrity controls for you to understand this concept in a little bit more depth. Number 1 is entity integrity. Entity integrity ensures that each record in the table is unique and can be uniquely identified. In the example that we use for the education students table, each student should have a unique student ID. This is typically enforced by setting the student ID as the primary key. This control prevents duplicate records and ensures that each student can be distinctly identified. The next one is referential integrity. This ensures that relationships between tables remain consistent. This means that foreign key values in one table must match primary key values in another table. In the orders table, each order should reference a valid customer ID from the customer table. This control ensures that every order is linked to an existing customer, preventing orphaned records. Orphaned record by itself is a whole new deal to understand. Next is the domain integrity. This ensures that the values entered in a column fall within the specified range of set values. In an employee table or employees table, the salary column should only accept positive number values. This control ensures salaries are realistic and meaningful, preventing invalid data entry. An employee cannot have a salary in negative. User-defined integrity is the next. To understand, this encompasses custom rules and constraints defined by the database designers to enforce specific business rules. In the bookings table for the travel agency, a rule might be set that a booking cannot be made for the data in the past. This control ensures that the bookings are only made in future dates, maintaining the logical consistency of the table. Check constraints are used to enforce specific conditions on the values in a column or a combination of columns. In the products table for an e-commerce store that I just discussed earlier, a check constraint might be used to ensure that the price column is always greater than 0. Otherwise, the store is going to have a loss. This control prevents negative or zero prices, ensuring all the products have valid pricing information. These data integrity controls work together to maintain the quality and reliability of the data in a database. They help prevent errors, ensure consistency, and enforces the rule and constraints that are critical to the functioning and database system. Hopefully this has given you in-depth understanding of data integrity controls. So this is another example. The create table statement includes the clause to specify how updates and deletes are processed when there are dependent tables. If a delete request comes for a record with dependent records in another table, the DBMS could restrict the delete, which means to disallow it, or it could cascade the delete so that dependent records with matching foreign keys will also be deleted, or it could set null, which means that deleting the primary key record will result in setting all corresponding foreign keys to be set to null. This would imply an optional one cardinality in the relationship. So let's look into this in a little bit more depth with few examples. Ensuring data integrity through updates is crucial to maintaining the accuracy and consistency in the data in the database. So we do validation checks, transaction management, referential integrity checks, and audit trail logging, as well as concurrency control. The validation checks, technically before updating data, we perform validation checks to ensure that the new values are correct and appropriate. When updating a customer's email address in a customer's table, the system should check that a new email address is in correct format, contains @ symbol, and the domain. This prevents invalid data from being entered. In transaction management, using transactions to group related updates together, a transaction ensures that all updates are completed successfully. If any part fails, the entire transaction is rolled back. When transferring funds between two bank accounts, the system should use a transaction to ensure that the amount is deducted from the one account and added to the other. If either update fails, the transaction is rolled back to maintain data integrity. Referential integrity checks ensure that the updates to foreign key value maintains referential integrity. This means that any changes to foreign keys must correspond to valid primary key values in related tables, which, when updating the department ID of an employee in the employees table, the system should check the new department ID exists in the departments table. This prevents orphaned records and maintain the consistency of relationships between tables. Audit trails and logging. Keep a record of all updates made to the database, including who made the change, when it was made, and what the old and new values were. In a hospital management system, every update to a patient's medical record should be logged. This includes the doctor's ID, the timestamp, and the detail of the change. This audit trail helps in tracking changes and ensuring accountability. Concurrency control is the implementation mechanism to handle concurrent updates, ensuring that multiple users updating the same data do not interfere with each other. In an e-commerce system, if two customers try to update the quantity of the same product in their carts simultaneously, the system should use locks on other concurrency control methods to ensure that the updates are processed correctly. This prevents data inconsistencies and conflicts. Apply same when we are booking the airline tickets. If all the seats are sold, if I do an update and let's say Matt does an update, it should have a locking mechanism applied that is called concurrency control. By following these practices, you can ensure that updates into the database maintain data integrity. These controls help prevent errors, enforce consistency, and maintain the reliability of the data even as it is modified over time. Changing tables. Let's look into this with a few examples. The alter command will be done after the table have already been created. For example, if you have an existing database, even one with actual data in it, you can modify table by adding or changing columns, removing columns, adding constraints, etc. If the data in the tables violate the constraints, you will be prevented from setting these constraints until after changing the data. So whereas create table is mostly a process that takes place during implementation, alter table often takes place during maintenance. Let's look into a few examples together to understand it in more depth. Altering a table is a common operation in database management system that allows you to modify the structure of an existing table. Let's look into a few examples. The first example is adding a new column on a table is a common alteration. Imagine you have a table for storing customer information, but you realize you need to start tracking customers' email addresses. You can add a new column called email into the table. This column will now be available for storing email addresses for each customer, enhancing the table's ability to capture more detailed information. Another alteration is modifying the data types of an existing column. Picture this, you have a table that stores product prices, and initially you used an integer data type for the price column. However, you can now realize that you need to store prices with decimal points. You can change the data type of the price column to a decimal type. This ensures that the table can accurately store and represent product prices. Dropping a column from a table is another type of alteration. Imagine you have a table for employee records and one of the column is fax number. Over time, you realize that fax numbers are no longer relevant for your business. You can remove the fax number column from the table. This helps keep the table clean and focused on the most relevant information. Renaming a column is another way to alter the table. Suppose you have a table for tracking orders and one of the columns is named as order date. You decide that purchase date is a more descriptive name. You can rename the order date column to purchase date. This makes the table more intuitive and easier to understand for users and developers. Lastly, adding a constraint to a table is an important alteration. Imagine you have a table for storing user accounts and you want to ensure that each user has a unique email address. You can add a unique constraint to the email column. This constraint ensures that no two users can have the same email address, maintaining data integrity and preventing duplicate entries. These examples illustrate how altering a table can help you adapt to changing requirements and improve the structure and functionality of your database. By making these modifications, you can ensure that your table remains relevant, accurate, and efficient. Removing the tables. Drop table statement allows you to remove tables from your schema. Drop table customer T. Tables will not be dropped if there are other tables that depend on them. This means that if any tables have a foreign key to the table being dropped, the drop table will fail that command. Therefore, it makes a difference in which order you drop the tables. Insert statement. As the last statement shows, it is possible to insert data into the table based on the query from another table. We will make more about select statements shortly. The insert operation is used to add new information into a table in a database. Imagine you have a table that for storing student information and you want to add new student. You specify the table you want to add to and provide the details of a new student like their ID, first name, last name, and age. The database then creates new entry in the table with these details. For example, if you want to add a student named John Doe who's 20 years old, you tell the database to insert this information into the student table. The database will create a new row in table with John's details. You can also add multiple students at once. Suppose you have two new students, Jane Smith, who's 22, and Mike Johnson, who's 21. You can tell the database to insert both of these students into a table in one go. The database will create two new rows, one for Jane and one for Mike. Sometimes certain details like student ID might be automatically generated by the database. In such cases, you only need to provide the other details like the first name, last name, and age. The database will handle the student ID for you. Additionally, you can copy information from one table to another. Imagine you have a temporary table with new students that you want to move into the main students table. You can tell the database to insert all the information from temporary table into the main table. The database will copy all the rows from the temporary table to the main table. These examples show how insert operation helps you add new information to your tables effectively and efficiently. Whether you are adding one entry, multiple entries, or copying information from another table to this table. Identity columns are introduced with SQL 2008. These are columns whose values automatically increment with each new insert. So an insert statement does not explicitly give a value for an identity column. This is handled automatically. Often primary keys are identity columns, but not always. Remember, referential integrity rules will control whether a delete actually happens. The restrict, cascade, and set null constraints will determine how to handle the orders for a deleted customer. So removes from the row table, deletes certain rows, delete from customer T where customer state is HI. It might be Hawaii. Delete all rows where delete from customer T is another example. For this update, we know that it will affect only one record in the table. How do we know this? The answer is because product ID is the primary key which must be unique. So there can be only one product with product ID is equal to 7. However, many times update and delete affects many records. For example, delete from customer T where customer T state is Hawaii or HI affects all customers from Hawaii. The merge statement was introduced in SQL 2008 to makes updating a table easier. Many database applications need to update master table with new data. A purchase T table, for example, might include rows that data about new products and rows that change the standard price of existing products. Updating product T can be accomplished by using insert to add the new product and update to modify product standard price in an SQL 1999 DBMS. The SQL 2008 compliant DBMS can accomplish the update and insert in one step using merge. The merge is based on a query select and perform updates on matched records and inserts on unmatched. Merge into product T as prod using whereas select product ID, product description, product finish, product standard price, product line ID from purchases T as perch on, and then this list goes on the screen. It is given to you to look at. The schema definition. All of this has to do with physical database design. Let's look into this with few examples. Let us look into some of the examples that I discussed earlier with you to understand what schema definition is. It is a crucial part of database design where you define the structure of your database, including tables, columns, data types, and constraints. First, consider a simple library system. To define the schema for the system, you might create tables books, authors, and members. The books table could have columns like book ID, title, author ID, and the publication year, and the authors table could include author ID, first name, and last name. The members table would have member ID, first name, last name, and the join date. This schema defines the basic structure and relationship needed to manage a library. Next, imagine a hospital management system. The schema for this system could include tables like patients, doctors, and appointments, as we discussed earlier. The patients table might have columns such as patient ID, first name, last name, date of birth, and contact information. The doctors table could include doctor ID, first name, last name, specialty, and appointments. Table might have appointment ID, patient ID, doctor ID, appointment date, and appointment time. The schema helps manage patient records, doctor information, and appointment scheduling. For the e-commerce platform that we are discussing, the Pine Valley, however, if we are looking into another e-commerce platform, the schema definition could involve customers, products, and orders as tables. The customer table might include customer ID, first name, last name, email, and address. The products table could have product ID, product name, description, price, and stock quantity. The orders table might have order ID, customer ID, order date, and total amount. The schema supports management of customer information, product catalogs, and order processing. In the travel agency system that I discussed, we can have tables customers, flights, and bookings. The customer table has the column customer ID, first name, last name, email, and phone number. The flight table has flight ID, departure city, departure time, and arrival time. Bookings table has booking ID, customer ID, flight ID, booking date, and seat number. This schema helps manage customer information for flight details. That is happening even till today, like Delta Airline, American Airline, or United Airline. The entertainment platform, as mentioned earlier, the schema definition could include tables like users, movies, and reviews. The users table might have columns such as user ID, username, email, and password. The movies table could include movie ID, title, genre, release year, and director. The reviews table has review ID, user ID, movie ID, rating, and comment. The schema supports the management of user accounts, movie catalogs, and user reviews. These examples illustrate how schema definition sets the foundation for a database by specifying tables, columns, and relationships needed to store and manage data effectively. Select statement. This statement includes many features that allow you to perform sophisticated queries. You can specify conditions for rows to be included in the results. You can choose which columns from these rows could be included. You can either get detailed data or get aggregate results such as sums and averages. You also have many options in how to sort and format results. Select from, where, group by, having, and order by are a few examples. The where clause includes one or more conditions. A condition is a test that for each row in the table is either true or false. Only those with true results are permitted in the result set of the query. Select product description, where product and product standard price from product T, where product standard price is less than 275. This is an example. The comparison operators include equal to, greater than or equal to, less than or equal to, not equal to, or not equal to altogether. Select example using an alias. Aliases are useful. They can often save only typing time when writing the query. Select cust.customer name as name, cust.customer address from customer underscore v cust, and cust is technically customer name now, where name is equal to home furnishing is another example. Using a function. Using a count aggregate function to find totals, select count star, count everything, from order line T where order ID is 1004. So find out all the orders which are given under the order ID 1004. So with aggregate function, you can't have single value columns included in the select clause unless they are included in the group by. The most common aggregate functions are count, sum, and average. When the above query gives a number indicating the total number of order line records associated with the order number 1004, that's how the answer comes to you. Select example Boolean operators and, or, and not operators for customizing conditions and where clause. Let's look into this in a little bit more in-depth examples. The select command in SQL is used to retrieve data from database. Boolean operators like and, or, and not are used to filter the results based on specific conditions. Consider a scenario where you want to find all employees who are both managers and have a salary greater than $80,000. You would use the AND operator to combine these two conditions. The query would look for employees where the job title is manager and the salary is greater than $80,000. This allows you to retrieve a list of high earning managers from the database. Next, imagine you want to find all products that are either in electronics category or have a price less than $50. You would use OR operator to combine these conditions. The query would look for products where the category is electronics or the price is less than $50. This helps you retrieve the list of affordable products or those in the electronic category only. In another example, suppose you want to find all customers who are not from New York region. You would use the not operator to exclude customers from New York. This query would look for customers where the region is not New York. This allows you to retrieve a list of customers from all other regions. You would like to see that how many people are spending outside of New York on an e-commerce platform, and to compare and contrast what spending the New Yorkers are doing, because you have found already all New Yorkers and now you're trying to compare all who are not from New York to make a informed decision. Consider a situation where you want to find all orders that are placed in the last month and have total amount of greater than $100. You would use the AND operator to combine these conditions. The query would look for orders where order date is within the last month and the total amount is greater than $100. This helps you retrieve a list of recent high value orders. Lastly, imagine that you want to find all students who are either in a computer science department or have a GPA greater than 3.5, but not both. You would use the combination of OR and NOT operator. This query would look for students where the department is computer science or the GPA is greater than 3.5, but not both conditions simultaneously. This allows you to retrieve specific subset of students based on this criteria or these criteria. These examples illustrate how Boolean operators can be used with the select command to filter and retrieve data based on the complex conditions. They help you refine your queries to get the exact information you need from the database. So by default, an AND operator or operation takes place before the OR. So only tables over $300 are included, and via the and these are then combined with all desks no matter what price via the or. So again, there is a Venn diagram is used in this, and Venn diagram is technically the diagram that we use in the set theory or set membership. So this is pretty much the implementation of set theory in the database using the Venn diagram for as an example for you. So with parentheses, these override the normal precedence of Boolean operators. Select product description, product finish, product standard price from product T, where product descriptions like the percent sign desk or product description like percent sign table and product standard price greater than 300 as we discussed earlier. With parentheses you can override normal precedence rule. In this case parentheses like or take place before the and. Sorting results with order by clause. Sort the results first by state and within the state by the customer name. So select customer name, customer city, customer state from customer T, where customer state in Florida, Texas, California, Hawaii. Order by customer state, customer name. Note the in operator in this example allows you to include rows whose customer state value is either Florida, Texas, California, or Hawaii. It is more efficient than separate or conditions. So let me share all these clauses, the and or, before I go in the order by, in a little story way. So once upon a time, there was a charming little bookstore called Page Turner's in the heart of the bustling town. The owner, Emily, was passionate about books and loved helping her customers find the perfect read. To manage her inventory and customer data, Emily used a database system. One day, Emily decided to run a special promotion to attract more customers. She wanted to send personalized offers to her loyal customers who had made multiple purchases and lived in a town. To find these customers, Emily used the AND operator in her SQL query. She wrote the query to select customers who had made more than 5 purchases and whose addresses was in the town. This query helped Emily identify her most loyal local customers and she sent them special discount coupons. So the query could look like select star from customers where purchase count is greater than 5 and address is equal to the town where the Emily's store is. Page Turner as a store. Few weeks later, Emily noticed that some of her best-selling books were running low in stock. She wanted to restock these books quickly to ensure they were always available for her customers. To find out which books needed restocking, Emily used the OR operator. She wrote a query to select books that either had less than 10 copies in stock or were in the bestsellers category. The query could be like that. Select star from books where stock is less than 10 or category is equal to bestsellers. This query helped Emily identify the books that needed immediate restocking and she placed an order with her suppliers. As the holiday season approached, Emily wanted to send special newsletter to her customers who had either purchased books in the fantasy genre or had spent more than $100 in the past year. To find these customers, Emily used combination of and or operators. She wrote a query to select customers who had either purchased books in the fantasy genre or had a total spending greater than $100 in the past year. So this query could look like select star from customers where genre is equal to fantasy or total spending is greater than $100 and the year is equal to current year, which can be 2024. This query helped Emily identify the customers who were most likely to be interested in her holiday promotions, and she sent them special newsletter with exclusive offers. Through the use of and or operators in her SQL queries, Emily was able to manage her bookstore more efficiently, target the promotion effectively, and keep her customers happy. The story of page turners shows how Boolean operators can be powerful tools for retrieving, analyzing the database. And let's now look into another story for order by clause. As the holiday season promotions were in full swing, Emily noticed that her bookstore was attracting more customers than ever. She wanted to make sure that her best selling books were prominently displayed to catch the eye of her customers. To do this, she needed to know which books were the most popular. Emily decided to generate a report that listed all the books in her inventory sorted by the number of copies sold. She wanted to see best selling books at the top of the list so she could prioritize their placement in the store. To achieve this, she used the order by clause in her query. This clause permitted her to sort the results of her query based on the number of copies sold in descending order, meaning the books with the highest sales would appear first. With the sorted list in hand, Emily rearranged her bookstore to feature the best selling books more prominently. She placed them on eye level shelves and created attractive displays to draw customers' attentions. This strategy proved to be very effective as customers were more likely to notice and purchase the popular books. Emily also wanted to send personalized thank you notes to her most loyal customers. She decided to generate a list of customers sorted by the total amount they had spent in her bookstore over the past year. By using the order by clause, she could sort the customers by their total spending in descending order, ensuring that her top customers appeared at the top of the list. Emily wrote heartfelt thank you notes to her top customers expressing her gratitude for their support. And the story goes on. So the continuation of the story that I shared with you for and or illustrates how order by clause can be used to sort data in database, helping to make informed decisions and improve business operations. By sorting the data, Emily was able to prioritize her best-selling books, reward her loyal customers, and analyze her bookstore's performance effectively. So categorizing results using group by clause, I would suggest you to look into this scalar aggregate and vector aggregate in the reading that has been assigned in terms of the book. Here you can look at the example as the vector aggregate. It will return the number of customers from each state. This query will return the name and the count of customers from all states that actually have customers. If we all wanted was the total number of customers across all states, we could do this scalar aggregate query, select count star from customer T. This query will return single value, which is total number of customers. That would be sum of all individual numbers returned from the aggregate query displayed in this slide. The having clause restricts which groups will be returned in a vector aggregate query. It is like where clause but operates in a groups, not individual rows. The select clause specifies which columns in return, and the from clause specifies the table these came from. The where clause specifies conditions that determine whether the row is returned in the results. Group by and having by clause for aggregate queries, and order by determining sorting. Next, note the queries can also include subsequent subqueries, and you may see select inside another select. So this work is protected by United States copyright laws. Please make sure do not disseminate outside of the university. Happy learning. See you in the next lecture. And now we'll go for a break.